Take a look around at the roads, bridges, and buildings that make up daily life, and you'll notice they nearly all share a single ingredient. And it isn't steel, timber, or glass. It's concrete. Plain, gray, unglamorous concrete. Humanity pours so much of it annually that if you gathered it into one continuous river, that river would run from the Arctic Circle to the southern tip of South America. That's not a flourish for effect. That's just the raw arithmetic. Concrete ranks as the second most consumed substance on the planet, trailing only water. Sit with that for a moment. More than oil. More than steel. More than lumber combined. Only water beats it, and the margin isn't close. Because of that, the entire construction industry has organized itself around this one material for over 100 years. Cranes, blueprints, and building codes across the globe simply treat concrete as the default choice, the material you reach for unless there's a specific reason not to. But here's a detail most people never encounter. Producing concrete pumps an enormous volume of carbon dioxide into the atmosphere. Not a trivial amount. Not a footnote buried in a report somewhere. The cement sector alone, just one component of concrete, accounts for roughly 8% of humanity's total greenhouse gas output annually. That exceeds the combined emissions of every aircraft currently flying. It comes close to matching the output of every car and truck on the road worldwide. So when a group of Chinese researchers quietly published findings in 2025 claiming to overhaul the core process behind concrete production, and engineering teams across Germany, Japan, and South Korea began racing to reproduce it almost immediately. That was a development worth understanding properly, not just skimming past. If you like watching how technology quietly rewrites the rules of the world, hit like and subscribe so you catch the next one. Let's dig into how this actually unfolded, because the roots of the story go back further than most people assume, long before anyone was talking about carbon footprints or emissions targets. To grasp why this breakthrough carries so much weight, you first need to understand why the problem went unsolved for so many decades. It wasn't for lack of trying. It's that concrete happens to be one of the most cleverly effective materials humans have ever engineered. And altering something already this refined is remarkably difficult to pull off, without breaking what already works. It's inexpensive enough that even lower-income nations can deploy it at massive scale. It's tough enough to support entire skylines. It can be shaped into virtually anything an architect can imagine, poured wet and left to become whatever the design calls for. It sets and hardens without any special intervention, needing no curing oven or chemical trigger. Unlike steel, it doesn't corrode. Unlike wood, it doesn't decay. Unlike glass, it doesn't shatter under stress. And it endures for decades, needing almost no upkeep. Through most of human history, nothing else offered that entire package at once, which is exactly why nobody seriously questioned it for so long. Engineers favor concrete because, after generations of real-world use, its behavior is thoroughly understood. How it holds up under strain, in bitter cold, under massive loads, across years of wear and tear. Builders favor it because raw materials for it exist almost everywhere geographically, so supply is rarely the bottleneck. City planners favor it because once poured, it rarely needs to be revisited or replaced. The entire field of civil engineering essentially assumes concrete's existence and predictable behavior as a starting point, a kind of silent foundation underneath the whole profession. The actual complication is buried inside its chemistry, and no amount of clever engineering easily removes it. Producing cement, concrete's essential binding agent, requires heating limestone beyond 1400 degrees Celsius. At that heat, the stone itself chemically decomposes and releases carbon dioxide as a direct byproduct of the reaction. This isn't a consequence of dirty power sources. Even if the kilns worldwide ran on flawlessly clean electricity, the stone itself would still release massive quantities of carbon. The emissions are woven into the chemical process itself, not something you can simply swap out for a greener power source. Now scale that up to how much cement the planet actually consumes. China alone, across just 2011 through 2013, used more cement than the United States consumed throughout the whole 20th century. Not across a generation, not across a decade, across 2 years. Whole cities rose from open ground. Highways stitched together regions that previously had none. Bridges spanned rivers that had never before been crossed. That construction pace pushed worldwide concrete demand to heights nobody would have predicted just half a century earlier. For years, researchers nibbled at the edges of the issue. Some tested swapping portions of cement for industrial leftovers like fly ash or slag. Others engineered geopolymer concretes using entirely different chemical bonding agents. A few pursued capturing carbon directly at the cement plant itself. These attempts offered incremental gains, but none reshaped the underlying economics enough to spread worldwide. The basic sequence, mix, pour, wait for it to set, remained virtually unchanged, generation after generation. The question nobody had really pursued was almost embarrassingly simple. What if the fix wasn't about altering the ingredients, but about what happens to the mixture the instant it leaves the mixer? Freshly mixed concrete isn't solid at all. Moments after mixing, it's a heavy, saturated slurry filled with water, pockets of trapped air, and loosely scattered particles of cement and stone. The standard approach is to pour it into a form and let time pass. Gravity contributes to some settling. Vibrating equipment nudges the process along. Eventually, the particles settle into place. Moisture gradually escapes, and the mixture solidifies into its intended shape. That basic method has barely shifted across generations of builders. A joint research team from Tongji University, the China Building Materials Academy, and Shanghai Jiaotong University tried a different path entirely. Rather than relying solely on gravity and patience, they applied mechanical force directly to the wet, still workable concrete, somewhere between 5 and 15 megapascals, comparable to the pressure generated inside an industrial hydraulic press, squeezing the mixture inward from every side rather than letting it settle passively on its own. The internal transformation was dramatic. The particles were compacted so forcefully that leftover water and trapped air were pushed out with nowhere else to go. The mixture turned noticeably denser almost immediately, similar to the contrast between a loosely heaped mound of sand and a tightly compacted block of stone. Overall porosity, the share of the material's volume made up of tiny gaps and pockets, fell by roughly 45% compared with standard concrete. That shift matters enormously, because those microscopic gaps are the origin point of nearly all concrete failures. Cracks initiate at voids. Moisture penetrates through voids. Salt and seawater compounds travel through them until they reach the embedded steel reinforcement, sparking corrosion that can hollow out a structure from within. Freeze and thaw cycles cause damage, because trapped water inside a void expands as it turns to ice. Shrink those gaps, and you eliminate most of concrete's long-term vulnerabilities in one stroke. But the most consequential shift happened at a boundary few people even know exists. Inside a piece of concrete, there's a microscopic interface where cement paste meets each individual chunk of aggregate stone. In ordinary concrete, that interface is actually the structure's weakest point, looser and more porous than either the paste or the stone alone, making it the first location where cracks typically originate under stress. Under this new pressurized process, that interface tightened substantially, with as much as 35% fewer voids compared to conventional mixtures. The chain's weakest link got noticeably stronger, closing off the pathway that usually starts the failure process. The laboratory numbers were remarkable. Compressive strength rose by more than 80% in the samples exposed to the highest pressure. Resistance to water penetration, freeze-thaw cycling, and chemical corrosion all improved meaningfully across the board. And here's the piece that made engineers take notice. The team accomplished all of this without introducing a single new component into the mix. No pricey additives, no exotic materials, no altered formula. The exact same raw ingredients, simply processed differently, produced a fundamentally superior result. The research group then took an unusual step. They released every underlying data set publicly. Raw spreadsheets, high magnification microscope images, force and displacement readings from nanoscale mechanical testing, all downloadable under an open license. In an industry built around guarded methods and inaccessible research, that level of openness was almost as striking as the findings themselves. And once other engineers could independently verify and reproduce the results, real momentum began building behind the discovery, moving it out of the theoretical and into something companies could actually plan around. While this concrete story was playing out in academic journals, a separate technology was advancing in parallel. One focused not on how concrete gets produced, but on whether certain buildings need much concrete at all. It's called BCore, engineered by Broad Group, a Chinese firm with a history of accomplishing things in construction that most people would assume are unrealistic on paper. The panels appear straightforward at first glance. Two thin steel outer layers separated by a precisely engineered grid of hollow steel tubes arranged in a geometric lattice, something resembling the inside of a waffle iron, but manufactured to tolerances measured in fractions of a millimeter. The concept borrows straight from aerospace design, the same principle that lets an aircraft body remain extremely thin yet extraordinarily strong by spreading stress through a structured lattice rather than depending on sheer material bulk. The steel layers manage tension and compression forces. The tube lattice handles bending and torsion. Combined, they create panels weighing under 1/10 of an equivalent reinforced concrete slab while supporting comparable structural loads. Broad Group had already made headlines in the early 2000s after assembling a 30-story hotel in just 15 days using modular steel building methods. BCore takes that concept a step further. The panels connect using robotic fastening systems, so an entire floor can be completed in a matter of hours rather than days. In 2025, workers assembled a 10-story structure in Chengdu using BCore modules in under 30 hours. Nobody was cutting corners to hit that number. The system is simply built for rapid assembly, in the same way flat-pack furniture is engineered to go together without specialized tools. What elevates this beyond a mere curiosity is its performance during earthquakes. Buildings located in seismic zones face an inherent challenge. Traditional concrete structures carry substantial weight, and heavy structures generate enormous forces when the ground shifts beneath them. Forces the building then has to absorb somehow. Lighter buildings constructed with BCore panels redistribute and absorb those forces in a fundamentally different way. And seismic trials showed the panels handling vibration and shock with a resilience conventional concrete framing genuinely couldn't match. In regions where earthquakes pose a persistent threat, which describes a substantial share of the world's most heavily populated areas, that isn't a small footnote. It's a core safety benefit that could change how those cities are rebuilt. Pressurized concrete and BCore tackle two distinct challenges, yet they move in the same overall direction. One makes the concrete that does get poured considerably stronger and cleaner. The other cuts down how much concrete a structure requires in the first place. Combine them, and their joint effect on cost, construction speed, structural weight, and emissions dwarfs what either innovation achieves independently. That combination is precisely what drew the global construction industry's attention so quickly. Innovation within construction rarely moves fast. Building codes take years, sometimes decades, to update. Major firms proceed cautiously, since errors involving structural materials carry consequences measured in human lives, not merely financial losses. So when worldwide interest in both technologies picked up speed within months of the 2025 publication, that signaled the industry recognized something genuinely unusual was unfolding, something worth moving quickly on despite the usual caution. 34 international patent families now reference the original Chinese research, with filings originating in Germany, Japan, South Korea, and the United Kingdom. These aren't passing academic mentions. They represent companies and research alliances committing real legal and financial resources to the technology. In 2026, China shipped 12.4 million metric tons of carbon-cured concrete additives to the United States, the United Kingdom, and Southeast Asia, a tenfold jump from just 2 years prior. Lafarge-Holcim, among the largest cement producers globally, signed a 5-year licensing agreement with Beijing Cement Group to adapt BCore for European prefabricated building projects. In Germany, a research consortium conducted live pressurized concrete deck trials on an actual highway project near Berlin. Japan's Obayashi Corporation launched a collaborative research initiative with Beijing University of Civil Engineering, aiming for substantial cement reductions in construction, tied to the Osaka Expo. South Korea's Hyundai Engineering revealed plans to build a domestic BCore panel manufacturing facility as part of its smart city development strategy. What's fueling all this isn't goodwill, it's arithmetic. In places where carbon emissions carry taxes or caps, a 40% drop in cement usage translates directly into reduced regulatory expenses. In virtually any market, lowering the cost of your priciest ingredient while simultaneously strengthening the final product isn't just a fad. It's a competitive edge no serious company can afford to overlook. As one R&D executive framed it, this isn't about chasing a trend. It's about remaining viable in a market that's about to shift under everyone's feet. The real-world testing that preceded this wave of corporate interest was essential in building trust. Along the Pingjiang River, 150 meters of bridge deck, built using the new pressurized concrete, were tracked continuously for 12 months through embedded strain gauges and moisture sensors. The measured compressive strength averaged 61 megapascals, aligning almost exactly with laboratory predictions. No visible cracking. Consistent moisture readings across the entire year. Every measurement from that monitoring period sits in a public archive, downloadable by any engineer wanting to verify it independently for themselves. In Shanghai, prefabricated BCore wall panels deployed in a pilot housing development delivered a 15% boost in thermal insulation and needed far fewer repairs after installation compared with conventional prefabricated panels. The engineers behind that project didn't select the material for environmental optics. They chose it because it was sturdier, cheaper, and backed by verifiable data. That particular mix, open science, real-world validation, and a clear financial case, is what sets this moment apart from earlier occasions when people claimed concrete was on the verge of transformation and nothing actually changed. The projected scale of this shift is almost difficult to grasp until you remember just how much concrete the world actually produces. Lifecycle modeling suggests that converting just 30% of new structural concrete worldwide to this pressurized process could reduce annual carbon dioxide emissions by roughly 850 million tons. For context, that surpasses everything Germany emits annually across its power plants, factories, vehicles, and farms combined. A single process shift applied to under a third of global concrete production. Delivering an impact of that magnitude is not a small claim to make. Still, turning a promising laboratory result into a worldwide standard is a lengthy journey, and it's worth acknowledging honestly where that journey gets complicated. Building codes across most nations update on timescales spanning years, sometimes decades, moving deliberately slowly because structural failures carry costs that go far beyond money. Any country hoping to adopt this at scale needs its own independent verification under local conditions, its own regulatory approval pathway, and its own skilled workforce capable of operating pressurized casting equipment reliably. China can share the underlying blueprints, but every other nation still has to do the work of localizing them. There's also the matter of existing infrastructure. Pressurized casting demands equipment most current concrete facilities simply don't own. Upgrading existing plants or constructing new ones represents a significant capital outlay. For large construction firms in wealthier economies, that investment likely pays off quickly, given the savings on cost and compliance. For smaller builders in developing economies, that barrier could prove far steeper, raising a legitimate question about whether this innovation actually reaches the regions that most need affordable, lower carbon construction. None of these obstacles undermine the underlying science, though. They simply mark the distance between what's technically achievable today and what will genuinely unfold at scale. Bridging that distance is as much a matter of policy and investment coordination as it is a technical hurdle. The researchers behind this 2025 publication handed the world a functional tool. Whether the world adopts it at the pace the climate crisis demands is an entirely different matter, one that depends far more on politics and money than on chemistry. What's undeniable is that, for the first time in a long while, the core process of producing and using concrete is genuinely shifting, not at the periphery, not confined to lab settings. Inside actual structures that actual people rely on right now. That's genuinely new. And given that concrete trails only water as humanity's most consumed material, shifts in how it's produced rarely remain small for long. If this video shifted how you think about something you walk across and live inside daily, drop a like and subscribe for more coverage of the technologies quietly reshaping our world. Turn on notifications so you don't miss the next one. And I'd love to hear from you in the comments. If a breakthrough this significant was sitting in plain sight for decades, what other obvious solutions do you think are still waiting to be noticed?